Hi, this is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome to Module 3 of Industrial Energy Efficiency Process Cooling. We'll talk this time about evaporative condensers, and this is the first of 2 lectures in this module. So we've already spent quite a bit of time looking at the thermodynamics of the vapor compression cycle, which is the core of all refrigeration systems. And the core of this is that the refrigerant in a very low pressure absorbs heat from some surrounding area, and it does that by evaporating, thus picking up the latent heat of fusion of that matter, and then the vapor, after it's evaporated, is compressed to a higher pressure and a higher temperature, and that's how it rejects that heat that it has just picked up in the cooling space. And it does that by condensing, and it does that in obviously the thing called the condenser. And in an industrial system or commercial system, these condensers are usually rooftop units. They have fans associated with them, and often for these very large units, they have a lot of water involved in it to help with the cooling process, and that's what we're going to be talking about. So this is just kind of a little cartoon where I'm showing what these things look like when you go visit them. So in a large system, the compressor room has lots of these very large machines and lots of piping. The rooftop unit is where the condenser is. Then there's a metering device that's usually right next to the evaporator, and it's usually not even visible, or you have to really go looking for it. And then the evaporator is the thing that's blowing cold air, usually in the freezer or the cool, whatever the cool space is we're dealing with. So as I mentioned, these condensers tend to be rooftop units, and they can be either just purely air cooled, in which case we call them dry or dry cooled units, or they can have evaporation involved in it. So you spray water on it, and as the water evaporates, it pulls more heat away. The home air conditioning systems are universally dry. They're just air cooled. But as you get greater capacity, we find it's worth developing and investing in the infrastructure required to use water. And so these things are called evaporative condensers, which sounds kind of funny, right? Because it's both evaporating and condensing are 2 different things, but we're evaporating the water and condensing the refrigerant. And in a previous lecture in the module, we showed some pictures of what these things look like. Here's a typical one here on the left. I got this from Johnson Controls. So the fans can be mounted at the bottom, like on the side of the device, or on the top like this. This is the more modern designs of these axial fans up here. The water gets circulated from a sump in the bottom to the top, where it gets sprayed down over what's called film material. And so you'll see this the pump usually on the side of the device, and a big vertical pipe where it pumps the water up. And then there's usually another place where the makeup water is supplied. So as the water evaporates, you need to be adding water into this thing. And this is more of a schematic over here on the right, where you'll see the refrigerant comes in after the compressor brings it up to a very high pressure and temperature, and it condenses here as the water evaporates off the coil. So it's worth taking a few minutes to think about what's happening, because the interaction between the compressor and the condenser is key for understanding the efficiency of these operations. So for heat to flow from the refrigerant to the outside world, it has to be hotter than that. That's one of those fundamental laws of heat transfer, right? Heat flows downhill. So the temperature of the compressor must be greater than the temperature in the environment, and the amount of that difference is called the approach. Okay, so for these big ammonia systems, 20 to 30 degrees is not unusual for an approach, but for the smaller systems, and particularly for the the halocarbons, the R22 and R134A and R410A, that tend to be more in the 10-degree range. So an evaporative condenser helps drive the heat transfer better because as the water evaporates, it absorbs the latent heat from the air around it, and hence it lowers the temperature. And as the temperature of that airstream is lower, it's easier to pull the heat out of the tubes and the fins surrounding the refrigerant. So we can lower the temperature. If it's 90 degrees outside, by spraying water on it, we get a cooler environment. But there's a limit to that, and that's the wet bulb temperature. So I think it's worth kind of taking a little time to review what that means. So dry bulb temperature is the temperature we think about, right? When the weatherman reports the weather on the news, when we measure something with a an IR gun, or just a thermometer in the air, we are reporting the dry bulb temperature. So there's two other temperatures that are associated with temperature of air, and it's associated with the dry bulb and the relative humidity, and they're called dew point and wet bulb. And the most important thing to remember is that they're not the same thing. They're very different. And we'll spend a few minutes to kind of talk about those differences. So here's the sort of conceptual control volume engineering sort of definition. So wet bulb is that if you have a control volume of humid air, of air with some humidity, and you evaporate water into it without adding any additional heat. In other words, so it's an adiabatic control volume, but you can add to it water, and it evaporates then to the point where you get the saturation, 100% relative humidity. Then the process of evaporating that water will have absorbed heat from the control volume, and the resulting mixture would be lower, right? And that's the wet bulb temperature. The dew point is looking at it from a control volume that's not adiabatic. In other words, it's a control volume where we don't add or remove any water, but we do remove heat. So we're lowering the temperature by removing heat from that control volume, from the mixture. And then you get to a point where water starts to condense, where you basically hit 100% relative humidity from that direction, and then beyond that the water condenses. That's called the dew point temperature. Okay, so it's worth spending a little time thinking about that. Here's everybody's friend, the psychrometric chart, right? This talks about the relationship between temperature, wet bulb temperature, dry bulb temperature, dew point temperature, and relative humidity. So all these things are out here. We got temperature lines showing along here. We can read dry bulb temperature along the bottom. Along this curve line, we can read both wet bulb and, here they're calling it saturation temperature, but that's dew point temperature. Lines of constant enthalpy are these straight lines that go sort of diagonally from upper left to lower right. Lines of constant humidity ratio are going across horizontally. So let's take an example. 90 degree Fahrenheit, 40% relative humidity. Kind of a typical day in the southwestern part of the state, or most of the southern part of the state. Pretty dry, kind of hot, right? So the dry bulb temperatures along the bottom here, so there's 90 degrees along there, 40% relative humidity. These curved lines are the relative humidity lines. So right at that intersection is where we'll find our point, 90 degrees Fahrenheit, 40% humidity. So the question we want to answer is, what are the corresponding dew point and wet bulb temperatures for this condition? So to get to the wet bulb, we take a line of constant enthalpy, right? We're not changing, we're not allowing heat to transfer in and out of the control volume. So there's these slanting lines that go up, and we can read the temperature off of this curved line here, and we're saying it's between 70 and 75 degrees Fahrenheit, closer to 70. Let's call it 71. Okay. For dew point, remember, we do remove heat, but we keep the humidity ratio, the change is the same. So it moves along these horizontal lines. And here I see a line here that goes from our point to the temperature, the curved temperature line, and it shows up between 60 and 65. So the dew point's a lot lower than the wet bulb. Wet bulb's around 71, dew point's around 62-ish, right? So that's the results of this. So it's worth taking the time to really kind of get this straight in your head, because sooner or later you're going to have to look at this again, and you're not going to understand it. You'll have to go through it again. So take some time. There's a great calculator here at the University of Dayton website. A good friend and colleague of mine, Kelly Kissick, is the Industrial Assessment Center director there, and has put together some wonderful tools, and this is one of them. So I encourage you to go take a look at that. Okay, so now we kind of know why evaporative condensers are better because they take whatever temperatures we're stuck with in the environment and allows you to access a lower temperature environment to reject the heat into. And we know that that's good because heat is driven from higher temperature to lower temperature, right? So so one of the questions that's worth asking, and frankly I grappled with this as I fairly over the last 10 years started trying to understand exactly how these systems work, is what determines the pressure at the outlet of the compressor. Right? There isn't a gauge on, there isn't a knob on the compressor that says, hey, I want a higher pressure, I want a lower pressure. And the fact is, the pressure is going to be somewhat determined by the temperature at the condenser, and that's going to be determined by a combination of the environmental temperature and how much heat we need to move through there, right? And so it's a combination of these various factors that need to come together before we understand it. So let's kind of walk through this. Let's look at our thermodynamics. So you remember this TS diagram from an earlier module. And so 1 is the inlet of the compressor, 2 is the outlet of the compressor, 3 is the outlet of the condenser. So the condensing process goes from 2 to 3, right? And it's not all constant temperature. It starts at superheat, then comes down into saturation, then it's pretty flat. So I want you to think about that, and that's where the mass balance, that's where the energy balance has to take place. So we know that the rate at which we can remove heat is from the refrigerant is related to T3 minus T infinity. And I'm making a little simplification here because I just said temperature starts at superheat. Turns out even though there could be a pretty big temperature change, since it's all in the vapor, there isn't as much actual heat transfer that goes on at the higher temperature. So we'll just make a simplification and say all that heat transfer is happening at T3 minus T infinity. So that's the approach of the condenser. And U is this kind of overall heat transfer coefficient. And it's often UA, but I've simplified it here just U, right? And it's made up of convection and conduction and all the ugliness that goes around the fins and all that other stuff. So there's 3 ways to make Q dot bigger, right? Q dot is what we need to have happen, right? We can make the condensing pressure higher, which drives T3 higher. We can make the ambient pressure lower, and we do this in the evaporative system by driving the temperature in the condenser towards wet bulb. Or we can make U larger. And one of the things that's buried in U is it's a convective coefficient is in there, and that's driven by the velocity of the air across the tubes and across the fins. And so we can make the fan blow harder, right? So those 3 things are all kind of under our control. Now, from the same side, looking at the thermodynamic cycle, we know that Q dot is equal to the mass flow rate of the refrigerant times the difference between the enthalpy leaving the compressor and the enthalpy leaving the condenser. In other words, that's the enthalpy change across the condenser. So the bottom line is, it's a little hard to move the needle from this side of the equation. You really got to look at it from the heat transfer at the condenser. So equating these two, we can get a little bit insight into how these various processes interact and how that temperature of the condenser ends up being established, right? So imagine the left-hand side, something happens, maybe the fan gets a little slower or the approach is a little smaller. So that heat transfer happening from the refrigerant to the outside air gets a little bit smaller. And so to accommodate that, the mass flow rate through the condenser must be a little hotter, right? Because there's less heat being removed. And so the refrigerant gets hotter. The T3 goes up, right? When that increases the approach of the condenser, T3 minus T infinity, and thus increasing the heat transfer. So if you push one of these, something else is going to push back, right? It'll find an equilibrium. So in any given condition, there's really one temperature of the condenser that really makes it work, right? And it needs to establish itself. We can't just set that. Here's a kind of a cartoon sort of graph showing it. So on one end, I've got this sloping blue line, and that's how the Q dot, the heat needing to be rejected by the condenser from the thermodynamic analysis. That's how that varies with the condenser pressure. And on the orange lines, I show various heat transfer as a function of condenser pressure from the condenser standpoint, from the heat transfer rejecting the outside air. So these are the Q dot equals U T5. And as if U gets bigger, by say changing the fan speed, we jump to different lines, right? And so at any given fan speed, there is a condenser pressure set by the intersection of those two lines. So at the lowest fan speed or the lowest heat transfer characteristic, we're out here on the right hand side, and as we go up, we move it to the left. We get lower condenser pressures, and gives you some insight into that interaction. And it's important to get your head around this because it's key to understanding the efficient operation of these, and it's also not well described in the commercial literature. Like when you talk to the people who sell these things and even operate these, they have sort of a fuzzy idea of how it works too. So, or maybe they have a good intuitive feel, but they haven't really been able to talk about it. So being able to interact with people, like whether they're the maintenance managers or the refrigeration technicians or the plant engineers, is a huge challenge. And the better we understand these physics, the better equipped we'll be when we go talk to them. Okay, so condenser control. So how do these things work? Sometimes they're as simple as a little switch that when the condenser temperature or pressure gets to a certain threshold, it turns on the fans, right? But maybe they're multi-speed fans, multi-speed control. This is a great application for variable frequency drives for these really big units. If there's big shifts in outside temperature or big shifts in refrigeration capacity, and finally there's an algorithm for these things for really very efficient operations called wet bulb approach, which basically sets a target condensing temperature that's about 15 or 20 degrees above the wet bulb, and that basically makes sure we put the minimum amount of energy we have to get rid of the heat we want. So I gave you a reading assignment that comes from University of Wisconsin. They've got a great center on industrial refrigeration systems, and it's kind of highlights all these different kinds of evaporative condenser control and the kind of analysis you can do to minimize energy consumption. And that's what we're trying to do here. So that's the operation in a nutshell. Clearly, or what should be clear, is one of the big issues we're dealing with here is outside temperature, and that's not constant. So in the next video, we're going to look at how we make use of weather data that's available to us to make predictions about energy consumption or about energy savings for various steps. So that's it. Thanks a lot, and good luck with the problem sets.